Okay, so we're going to look at verifying or proving some trig identities. Remember, there are multiple ways to get to the right answer. There are lots of ways to do this, but just practice, start seeing some patterns, some things that tend to happen every time, or some good ways to start, and you'll get the hang of it the more you do of them. One tip, this is not a hard and fast rule, but if you begin with the more complicated side of the equation, like tangent theta, cosecant theta is more complicated than secant theta, and what your goal would be to rewrite this as what you know, get some things to cancel, and you'd end up with the less complicated side. Okay, so that's what we're going to do here. We know that tangent theta is sine theta over cosine theta. We know that cosecant theta is 1 over sine theta. And now we look at that, we're multiplying two fractions. We see that these cancel. We end up with 1 over cosine theta. And guess what 1 over cosine theta is? Secant theta. So we verified that tangent theta times cosecant theta is equal to secant theta. Okay, 1 over sine beta minus cosecant beta is equal to the opposite of tangent beta, secant beta. The fraction is obviously the more complicated looking side, so we're going to start there. Be careful, since the denominator is what has the subtraction in it. This cannot be split up. Like, we have split fractions where the numerator had a sum or a difference in it, but if a denominator has the sum or difference, you cannot do that, okay? So what we're going to do, we're going to rewrite this down here. We're going to leave the sine beta alone. And we know that cosecant is 1 over sine beta, right? Now, this is going to be a little funky looking because we've got this complex fraction. We've got fractions inside fractions with subtraction problems, all that fun stuff. I'm going to put this over 1, and I'm going to deal with the fraction work down in the denominator. So I'm going to have 1 over my common denominator between 1 and sine beta is sine beta. My second numerator is not going to change because my denominator didn't change. And the first one, I'm just going to do normal fraction stuff. 1 goes into sine beta times sine is sine squared beta, okay? Now I have 1 over sine squared beta minus 1 over sine beta. And when you do 1 over, that means the reciprocal, right? 1 over something is its reciprocal. So we're going to flip this, and we're going to get sine beta over sine squared beta minus 1. At this point, we still don't look anything like what we're getting to, but let's see what happens. Okay, so here's what I noticed. Sine beta in the numerator, not a whole lot I can do with that, okay? Sine squared beta minus 1. This looks like the fundamental theorem, the Pythagorean identity, where sine squared plus cosine squared equals 1. And we know that cosine squared is 1 minus sine squared. But this is sine squared minus 1. This is backwards. So we need to do that trick we talked about in the algebraic manipulation, where we factor out a negative and we do the little switcheroo. Remember, when you factor a negative and it's a subtraction problem, both those signs swap, so we can actually just write it in the other direction, okay? Now, we know that that is cosine squared beta. 1 minus sine squared beta is cosine squared beta. Now we're going to do another fraction trick. We're going to say that this was originally, we're going to keep that minus sign out there. We don't need to lose it. And we're going to do the cosine squared beta as cosine beta times cosine beta, both in the denominator, right? So I just sort of split this cosine beta into its two factors. Now, sine beta over cosine beta is tangent beta. And 1 over cosine beta is secant beta, which is what we were going for, okay? That is one that basically what you would have to do if I were doing this and I was just starting, I would start over here, I'd do my fraction stuff, and then as you get to things, you go, oh, that looks sort of like the Pythagorean identity. I need to reverse it and take the opposite. This right here is a fraction trick. Study that fraction trick. See what happens if we were to multiply this across, we'd get this, and then we finally get to something that gets us what we're looking for. All right, cosine squared alpha over 1 plus sine alpha equals 1 minus sine alpha. The fraction side is the more complicated one. What I'm going to do, I'm going to use my Pythagorean identity, and I'm going to write cosine squared alpha as 1 minus sine squared alpha. Notice we're using that one quite a bit. It comes up pretty frequently. Now, there's a couple of things we could do here. What I think I want to do when I look at this is a difference of squares, right? If you need to go back to that algebraic manipulation video and watch that, this is a difference of squares. I can factor that into 1 minus sine alpha times 1 plus sine alpha. Put it over 1 plus sine alpha. These cancel, and I get 1 minus sine alpha, which was my goal. So that one wasn't too bad if you recognize the Pythagorean identity and then recognize that that's a difference of squares. Another thing you can do, if you look at this one, both sides look bad. They both look horrendous. You can work on both sides of the equation until you get to something that's the same thing, okay? So what we can do, we can sort of draw a line through here, and we can work on both sides until we get something that is equivalent, okay? So if we look at the left side, we see sine squared tangent squared plus 1. I'm going to say that that is sine squared theta tangent squared theta, and 1 is sine squared plus cosine squared. Okay, so what happens then is I look at these two terms and I notice that sine squared theta is common to those two terms. So I'm going to factor it out, and I end up with tangent squared theta plus 1, and then this plus cosine squared theta is still just hanging out. Okay, this is a Pythagorean identity. It is secant squared theta. Okay, then I'm going to write that as 1 over, 1 over secant is 1 over cosine squared theta, right? Forgot my theta up here. So this is sine squared theta over cosine squared theta plus cosine squared theta. So I get tangent squared theta plus cosine squared theta, which is actually not too bad looking. Let's see if we can get the other side to match, okay? I'm going to do sort of the same thing here. This right here is sort of like from this step on, it's going to be very similar. When I look at these two terms, secant squared theta is common. So I'm going to take the secant squared theta out. I'm left with 1 minus cosine squared theta. I factored that out. And then this plus cosine squared theta is tagging along. So this is secant squared theta times sine squared theta plus cosine squared theta. And I actually, I've been using the book here. We could actually stop right there, couldn't we? because right here, look, sine squared theta, secant squared theta plus cosine squared theta, sine squared theta plus or times secant squared theta plus cosine squared theta. Wherever they match, whenever they match, they're done. They're equal, okay? You've got something that looks the same. The rest of this would look just like that. I'm not really sure. I was using the book to help me. I'm not really sure why the book went on and did down to this level. Once you get something that's the same, you're done.